No, that's just my water. I was filling, that's okay. All right, so pH measurements, right? This is the formula for calculating the pH. So it emphasizes the fact that as our hydronium concentration increases in solution, what happens to our pH?
The pH goes down.
pH goes down. Right? So as this gets bigger, meaning as more hydroniums are in solution, the lower our pH, the more acidic we get. So if we have a generic strong acid, and we put that in solution, we'll leave it that way. What happens to a strong acid in solution?
Dissociates completely.
100% dissociation. So we end up with our conjugate, which would be as a salt, depending on what else is there. But just in water, right, we're going to get 100% ionization. If we have a weak acid, how is that different in solution?
It doesn't.
Partial dissociation. So we have to use our double arrows, emphasizing that most of our acid is present in the molecular form as HA. And we only have maybe, 5% on average, depending on your concentration and your dilution and all of that, maybe only 5% dissociates over here. So the fact of the acid dissociating and or truly reacting with water, right? With a weak acid, we think of it more as an actual reaction with the water. We're increasing the hydronium in solution, therefore we're changing the pH and lowering that pH. So let's assume we have a solution of a strong acid and we measure our pH to be 1.0. If we dilute it 2 times, what do we expect the pH to change to? 1.3. Right, if it's strong, we're expecting a 0.3 change in the pH, and this is all was discussed in the bottom of our introduction background part on here. If we have a weak acid in solution, let's say our pH is maybe 4.2. If we dilute that 2 times, what do we expect to happen to our pH?
It should be less than 0.7.
We'll say 4.4 or 4.45, right? It's still going to change. It's going to get closer to neutral, but by less than the 0.3. And that's because as we dilute a weak acid, it's an actual reaction going on. As we dilute it, we're increasing the amount of water that we have when we dilute, right? If we increase this, what do we know is going to happen, or what can we predict is going to happen in a reaction?
More dissociation.
More dissociation. Le Chatelier says that it's going to force the reaction to the product side. So we're actually increasing the dissociation or percent ionization for that weak acid. So that's why we have a change, but not as big of a change, because we're actually increasing a little bit, but it's still weak. So if you have 2 samples and you're told one has a change of 0.3 when it's diluted and the other one has less than that, you can use that as a predictor of this one must be a strong acid, this one must be a weak acid. We see the same between a strong base and a weak base. So if you have a strong base and let's say your pH was 11.2, when you dilute 2 times, it's going to drop to maybe 10.9. It's going to change by 3, working its way towards neutral. A weak base, a pH of maybe 9.3 is going to change to maybe 9.1. Right? So the same type of change, just going towards neutral. Okay, any questions? keep moving along. Okay. As we look at, I'll erase this one first. Okay, let's assume we are mixing HCl, one of our strong acids, plus KOH, strong base. What happens when we mix the two together?
Well, they completely cancel. It's gonna get you salt and water. And if
Salt and water, right. So what's the name of that type of reaction?
Acid-base reaction.
Acid-base.
Neutralization.
Neutralization, yep, we're going towards neutral there, because in this case, the salt we form have neutral ions.
Yeah.
Now, if you by any chance had a strong acid, strong base where something wasn't neutral, should always be, then we'd have to do another think, but we're gonna look at that in a second. So strong acid, strong base, neutralization, you form a salt and water. If we have a weak acid, like our acetic, plus a strong base, double arrows because it's weak, what do we form?
A conjugate base, that's acetate ion plus OH.
Well, we're still going to have the same type of reaction. We're still going to form a salt plus water.
That's a buffer, right?
Right? Not a buffer. We're
Oh.
forming a salt plus water.
Okay.
It
Yeah.
might have some buffering capabilities, but we're not
Oh, but actually it's
adding,
salt
right?
and
We're
water.
adding, we're still
Yeah.
adding salt and water. But in this case, what do we have here? You mentioned the conjugate base, right?
At the end.
So here we have a particular ion that we know is going to react with water because it's from something that's weak. So in solution, that is aqueous. When we put that in water, which it's in water, right, it's going to want to reform its acid. Oh my gosh. And then we're going to have some hydroxide left over. So this is an example of a basic anion because it's increasing the basicity of the solution a little bit, right? Not much. It's still a weak conjugate base, but it can have that overall effect. So whenever you are working with a weak acid or a weak base, you have to think what ions are present in your salt, how they're going to interact with water, and that can affect the overall pH of your solution by a little bit. So that means it's good to review your strong acids, strong bases, weak acids, weak bases for this exam too, because you never know if they might give you a different one. But again, there's only 6 strong acids that you need to know. Everything else is weak. The only weak base you need for the means ammonia, everything else is considered strong. Yes. Okay. So when you did your lab report, right, it was all about setting up different types of solutions, diluting it. Did it change your pH? Did it not change your pH? Was it able to be affected by adding an acid to it? So let's add one more scenario before we move on. We go back to our weak acid in solution. Oh, I do that. 3O plus. I'm doing too many of these. Okay, so if we have our weak acid in solution, and let's say we have a certain number of grams of that acid, and we add a certain number of grams of our conjugate base. So we're mixing the two together. We're not just letting this react to form it. We're actually adding some of it together. What type of solution are we setting up?
That's the buffer.
That would be your buffer solution. Because we're controlling the ratio of these two in there so we can control the pH range that can absorb acid or bases that are added to it. So if you don't have a buffer set up, adding an acid's going to really change the pH. So I'm just making sure I've hit all the questions on the back of the report. So again, when you study and really get to finalize your preparation for this, read your backgrounds, look at your lab reports, make sure you can answer those questions on the back of those pages. And that you understand the data, because you might be given data, right, and have to interpret the data for things. So make sure you go through all of that. All right, any questions on pH measurement?
Is there going to be any I guess I can ask that. Okay. They're not going to ask about like the I can't think about the equation for the buffer.
Henderson-Hasselbalch?
Yeah.
You might find, like when you do the Ka or look at reactions, you might find an instance where you could use it. I don't know.
Okay.
I don't know. For the Ka, we will probably address that a little bit.
Okay.
Anything else about this lab? No? Okay. All right, the next lab was determining the equilibrium constant Ka for a weak acid, right? So whenever we see K, we know it's equilibrium constant. What is the formula for determining an equilibrium constant? It's always products over our reactants. If you see an A, that means we're talking about it specifically for an acid. So again, if we have a weak acid, which we focused on in this lab, and please, when you're writing your reactions, always include your charges on your ions. Don't start dropping those. So products over reactants, so our Ka is the concentration of, oh my gosh, our conjugate base, in this case, times the hydronium ion concentration over our acid. Do I include water?
No.
No, because it's pure, right? So we don't need to include the water on there. So just like with pH, we were able to relate concentration to pH. They were inversely related, right? As the concentration went up, pH went down. In this case, we can relate our concentration of hydronium to Ka, but they're going to follow each other. So as your concentration of your hydronium increases, your Ka is going to increase. So the bigger your Ka value, the more dissociation, so the lower the pH. Okay. As your Ka goes up, your pKa is going to go down, because pKa is the negative log of your Ka value. We don't use pKa in here a lot unless you come to the Henderson-Hasselbalch opportunity. So this whole lab was looking at determining your Ka and showing you also how you can relate Kas to the pH and the strength of your acid. So as your Ka gets bigger, you have a stronger acid, even within the weak acids. So remember that a Ka of 10 to the negative fourth is a bigger Ka than something that's 10 to the negative eighth. Right? So just remember those values, kind of work your way backwards there. Keep that in mind. The main part of this was doing your what happens in solution. Do you have just a solution, meaning it's an equilibrium problem, or are you actually having a reaction occur with these? So review how to do all these examples that were in this lab, right? As you read through your background, make sure you understand the differences between each of the examples that they gave in here, because they really emphasize, do you have an equilibrium? Do you have a reaction? Are you setting up a buffer? That type of thing. So when we look at the actual lab report, it's a pretty simple lab to do. If you remember, you were just taking pH of some solutions. So that part went well, and then you spent a lot of time doing problems, right? Lots of math for this one. So we started off the first one, you're just putting acetic acid in water, right? You have a certain solution of that. I think you had 10 mils of a 0.1 molar, and you measured the pH. So if it gives you the pH of, say, 2.87, what can we calculate from that?
The concentration.
Of
Hydronium.
hydronium. Which concentration? What we're starting with, what we're ending up with?
Equilibrium.
Equilibrium. Excellent, yes. So this can give us our hydronium concentration at equilibrium. So it's important to remember when we have these equilibrium constants, it's at equilibrium. So each of these concentrations are equilibrium concentrations. So if we know what we're starting with, let's say we have 0.1 molar of that, right? We can set up our ice tables to figure out what we have at equilibrium. In this case, we can actually get our value here.
Right.
So we're lucky these are all 1-to-1, so we're going to lose x, gain x, but we know what x is from here. So we can get this value, plug it in there, so we can determine each of our equilibrium pieces, plug it in and calculate our Ka. What happens if we have the same 0.1 molar, but the next step you dilute it? What do we have to do to determine equilibrium for everything? We're going to have a new pH. Maybe this time it's 3.4. What do we need to do if we dilute our original sample?
BCA table.
Not yet?
And once
We're going to have a new concentration if we dilute it. So C1V1 equals C2V2, right? It's just a dilution. We're not having a reaction. So maybe we're now at 0.05 molar, depending on how we diluted it. We would set it up the same way, calculate our new hydronium, subtract that out, and calculate our new Ka. Remember, when it's just your acid or base in water, it's always an equilibrium problem, ice table. So ice table is for equilibrium. You always use molarity when you do those calculations. What if we add a salt? Say we have 10 mils of 0.1 molar here, and we add 10 mils of 0.05 molar of our salt. What do we need to do? Do we use molarity still? What do we need to do for that?
This time we need moles.
105.
Is it a reaction going on though?
Yeah.
Do we have a reaction if we're just adding more of this to it?
Yes.
No, it's just
So-
an equilibrium.
So it will be like 0.05 plus x.
Yep, but we have to first calculate a new molarity
Yeah.
because we're diluting it in the process. Okay, so you would calculate a new
I see.
molarity because now you have 20 mils
yeah.
of that, and you would calculate a new molarity, right? But it's still in
Yeah.
equilibrium, so you keep your molarity there. Still plug your pH in here, but now you're adding a value to that there.
Okay.
You're going to end up with, well, we're still calculating your K, so never mind, I'm jumping ahead. Okay? If you have this and you dilute it, you just have to remember to add all the volumes up when you calculate your new molarities. Okay, it's still an equilibrium problem.
Okay.
Now, what if we have our weak acid and we're adding a strong base to it? Now we're going to end up with our conjugate plus our water on this side.
Now this is titration or neutralization.
Now we have an actual reaction going on. For that, we have to look at moles. So a reaction, we might use an ISA table. If your teacher used ISA, did anybody not use ISA?
We use,
No,
B-
ISA
we use
tables?
BCA. Yeah. It's kind of the same. BCA. So yeah.
BCA?
Yeah.
Before change and after? Okay. So BACA, what do you call it? What did you call it? Just BCA?
Just BCA.
BCA, okay. Moles, because it's an actual reaction. Reactions are based on stoichiometry, so you have to look at the moles that you have present. Okay? So you're going to have moles, you're going to have a change based on a limiting reactant, because one of these is probably going to be not the same. If they are the same, then you're only going to end up with your conjugate. In this case, let's just say we have 0.2 moles of this, 0.1 moles of that. Okay, so that makes our base our limiting reactant. So we would subtract 0.1, end up with 0.1 moles here. End up with 0 of our base, but we would add 0.1 moles of this. Okay, what type of solution do we have? We have an acid and its conjugate.
Now we have a buffer.
We've set up a buffer. So you could use Henderson-Hasselbalch at this point. If you choose to look at another ice table, you would have to convert these to molarities to move on. Okay. What if we have different situations? Say we have 0.2 moles of this and 0.3 moles of that. Now we've changed our limiting reactant, right? So now we're going to use up all of our acid. We'll have some of our base left over, and we have some of the conjugate produced. How do I determine information from this? What do I need to think about? What's important?
So the conjugate base is going to react with water to produce even more hydronium. So you have to add the hydroniums together and then find your
you have to look.
POH.
So whenever you do a reaction, you have to say, what do I have left over? How is that going to change anything?
So we have OH. We cannot check pH from OH.
Well, so this is a different problem where we're not
Okay.
not answering the same type of question with that.
Oh yeah, that's K1.
Yeah. Again, if you dilute it also, you just gotta, when you recalculate molarities if you need to, you have to make sure you take all of those volumes into consideration. Make sure when you look through your lab reports, pay attention, review how to calculate your percent error. That's something that people sometimes miss. It's one of those, it's been so long since we've done, we forget how to do. Make sure you review how to calculate your percent ionization as well. This one didn't really have any questions to answer. It was all math. Any questions about this one? So again, just remember, ice table, you have to be in molarity, and you might have to calculate a new molarity depending on what you've done. If you have a reaction, you can do an ISA, a BCA table. Just remembering you have a reaction occurring, so you have to look at what products do you have, what do you have left over? Do you need to do another ice table, or can you just use the data that you have? Okay, any Any questions about that one? Feel free to stop me. Just kind of plow on through. Okay, one last pH lab, titrations. So important thing to remember, titration is a process. Okay, it's a process of mixing an acid and a base together, or the base and the acid, depending on what you start with. So if we think of having an Erlenmeyer flask, yes, that's an Erlenmeyer flask, even if it doesn't look like one, you might have an unknown amount of an acid or a base in there. Let's start with an acid. Let's say we have some unknown molarity of an acid, which means we're going to have to add a base to it, and we're going to be looking for the end point, right? Usually by a color change or by the time we hit a certain pH.
Yeah.
So we have our color point, our color change. We know we've hit the end point. What is the end point approximately equal to?
The halfway of the curve, the pKa,
The equivalence point,
equivalence
right?
point,
The end
the-
point is going to happen really close to the equivalence point. We're not going to be perfect, but it's going to be near that equivalence point. What do we know happens at the equivalence point? What do we have present in solution? Of what?
Moles.
Same amount of moles of our base and our acid. So we're adding a known amount, a known volume, and we're adding a known molarity, usually of 1, and we're using that to calculate the molarity of the other, because we know the mole ratio. Generally, we try to get to 1 to 1, but it could be 2 to 1. So you use your mole ratio, you know how much of this you're adding, and you calculate that. So if we think about what we have in solution, we're thinking about a weak acid, for example. A weak acid might have an original pH of, 2.5. Just gonna make something up. So we have our weak acid in solution. We look for that halfway point. Trust me, that's in the middle. Okay, we're gonna pretend I'm not the best artist. That's in the middle there. Notice that our halfway point is above 7, right? If we had a strong acid, strong base, our equivalent point would be halfway up. That's what I was trying to say, halfway between that upper part. So we have our equivalence point. And at our equivalence point, we already said we have equal moles of our acid and our base. Notice for weak acid, it's above 7. Reminder from what we drew earlier. That's because we end up with a conjugate base that's going to react with water and increase our hydroxide concentration, because it's going to want to reform that acid. Okay, so that's why we're over that 7. So that's our equivalence point. And let's just say it's at 24 mils. What do we know about this region of the titration curve?
That's our buffer area.
Buffer area, excellent, yep. So our buffer area, or our buffer zone. What do we know is occurring at 12 mils?
The halfway.
Half equivalence point. What do we have present at the half equivalence point?
pH equals
Yeah.
pKa.
pH equals pKa. Why?
Because the log of the acid and the base is 0, so the
Yeah.
Henderson-Hasselbalch equation pH, what you're
So-
left with is.
At the halfway point, we have equal amounts of our acid and conjugate base. So that makes the log plus conjugate over the acid equal to 0. So pH equals pKa, we have equal amounts of the acid and the conjugate base. What do we have up here? Do we have a special name for the area at the top? We don't have a special name. Because up here, we have so much excess hydroxide that is determining what the pH is above that equivalence point. When we did this, why did we first have to standardize our sodium hydroxide solution?
Because it reacts with air and carbon dioxide and sodium carbonate.
We don't need to know that that's specific. We just know that sodium hydroxide absorbs, reacts with the CO2, maybe a little water vapor in the air. Meaning if you put solid sodium hydroxide in a weigh boat, it's going to continually absorb stuff from the air, which is going to make it heavier and heavier and heavier, right? So we can't get an accurate mass. So we make a solution up and we titrate it with a known amount of something that is very stable, and we can determine our concentration from that. So sodium hydroxide is not a primary standard purity substance. So we have to be able to calculate that initially. So again, practice your ICE tables, practice your BCA or ISA tables as well, because in different regions, you're going to have different things that you can do and different ways to calculate what you have. Be able to read and interpret titration curves. Be able to identify equivalence point, half point, halfway point, your buffer area, what the volume, if you're given volumes, be able to determine which part you have there. If it's a strong acid, weak acid, right? This we said was a weak acid. A strong acid would start out much closer to 0 or to 1, and you'd have that equivalence point at 7. If you're starting with a base, strong base will be close to 14. A weak base would be lower, maybe 12, 11, something like that, right? Again, same pieces of information, but now we have our buffer zone at the top, our equivalence points measured at the halfway here, and it goes down to the ends. Okay, so be able to identify those parts and to get relevant information off of those graphs. Double check sig figs when you're doing any type of calculations, especially when you're starting with a mass, right? In general, usually the mass will control your sig figs because we can usually get only 3 from our balances. Whereas your burette, you can sometimes get up to 4, like if you do 10.22 mils, right?
Sure.
So pay attention to what's limiting your sig figs and make sure you use correct ones as you do your calculations. If you are asked questions such as why is the pH at the equivalence point higher than 7 when you mix a weak acid and a strong base, don't say it's because it's a weak acid with a strong base. What does that mean? Be more specific. Say, when a weak acid reacts with a strong base, you're left with conjugate base, which can react with water, generating more hydroxide ions. Okay, make sure you give a complete answer. Use equations to help illustrate your words as well. If you are given a question like 3A and 3B, what happens if you record your mass incorrectly? How is that going to affect the molarity of the other thing, right? Think through the logic of, well, my molarity is moles per liter. If my mass goes down, my moles will decrease, so my molarity decreases, right? If you record a mass that's high, that's going to increase the moles. My mole ratio will say I have more moles of this, therefore my molarity is going to be too high. So work your way through the math logic. Does it matter let's say we have 0.3 moles of my acid in there. Does it matter if I have that 0.3 moles in 100 mils or 150 mils? Does my volume matter?
No.
Why not?
Because you have the same number of moles.
Right, because we're only care about the mole ratio.
Yeah, the water doesn't react.
Don't care about the molarity of what's present, just the number of moles. So the volume is okay. That's why it's okay to rinse down the sides of your container, to rinse off the point of the burette tip, because that little bit of water is not changing what you have present. Okay. Any questions from this one?
Yes.
Yeah,
Go ahead.
okay.
Okay, so on the half equivalence point,
Uh-huh,
the pH is equal to the pKa.
yes.
Why is that?
So if we think of Henderson-Hasselbalch,
Mm-hmm.
because at this point we have equal amounts of our acid and base,
Mm-hmm.
that makes this the log of 1. Log of 1 is 0.
Mm-hmm.
Therefore, we have pH equals pKa plus 0. So pH is equal to the pKa.
Okay.
And why
Alright.
wouldn't it be that at equivalence point if they were the same, if they're still equal?
This is moles of the acid to the base, not to the conjugate base.
Okay.
That was one of my questions. Okay.
Okay. Good, yeah, so equal moles, acid and original base.
Okay. And then we were talking about why we standardize. We were talking about standardize the NaOH first,
Uh-huh.
and then it's because we can't accurately weigh the sodium hydroxide because it's constantly reacting with what's in the air.
Within the air, yep.
But
So you can't get an accurate mass.
but when it's in solution, it's more stable. That's kind of the main point. It's more stable, and we can.
Right. Once it's in solution, you can much more accurately figure out how many moles you have present.
Okay.
Yes.
Okay. That
They
makes sense.
still recommend that you keep it covered. Like if you left it exposed to the air for a long time, it probably would change a little bit. That's why we keep those covered with your watch glasses usually
Yeah.
once you make them.
Okay.
Yeah. Good question.
Thanks. Okay.
Anything else?
Oh, yeah.
Yeah.
So with the, if it's a weak acid plus a strong base,
Uh-huh.
the pH is going to be above 7, right?
Yes.
Okay.
Because your conjugate is going to react with the water to form the original weak acid, leaving hydroxide ions. So this, even though it's a little bit, it's going to be added to what was present originally.
Okay, and if it was the other way around, if it was a strong acid and a weak base, it would be
Yes.
lower than 7?
Yes,
Okay.
you got it.
And weak acid, weak base, it'll be at 7, strong base.
Weak
We don't
acid,
really-
weak base, it's going to depend on what conjugate you form.
Okay.
So it just depends on which two you're mixing together.
Okay.
And which one has the stronger Ka or Kb values. You have to do more math for that.
Okay.
Anything else? All right, that was all the pH stuff. Let's tackle qualitative analysis. So because we have 3 labs of pH things, each one is weighted pretty equally. Because we have 3 labs dedicated only to qualitative analysis, that's going to be a little more heavily weighted on the exam. I think they said about 30% will come from the qualitative analysis part. But don't panic. People like to panic with qualitative analysis. It's not necessary. I promise. You find my notes and we will make it clear for you. Oh, they better be in here, or I will panic. I think I tucked them back in there. Thing, maybe. There it is. Okay. Looks like a lot of information. So, most important thing, do not waste your time memorizing this whole flow chart. You do not have to be able to reproduce this, okay? What you need to be able to do is explain the chemistry behind why group A precipitates when it does, why group B precipitates when it does, and why group C does what it does. Okay, we want you to understand the chemistry. Now that means you still need to know that initially we added ammonia with a little bit of acid. But you do not need to know that you used 1 mil of 6 molar ammonia plus 3 drops of 6 molar H. You don't need to know the detail, the amounts and the concentrations. You just need to know that we added aqueous ammonia to the original solution. Okay? You do need to know your confirmation tests. So you need to know that when you had iron isolated as an ion, that you added potassium thiocyanate and it produced this particular color solution, which confirmed that you had iron present. Or you need to know that calcium oxalate formed a white precipitate. Okay, so you need to be able to identify the colors, identify if it was a solution or a precipitate, and what you used to confirm that. Okay, there's only 9 of them. It's not that many. But you don't need to remember that you added 6 mole or whatever, or 3 grams of whatever. Okay? All right.
So we should know like barium sulfate, it forms white precipitate.
Mhm.
Okay, the color of the precipitate.
Yep, whatever that confirmation test was. All right. So we started with a mixture of 9 ions, right? They were in solution. Were they in solution all by themselves? Just cations
No.
floating around in solution? No. What did they have to have with them?
They had to have the conjugate or whatever.
The counter ion,
Yeah.
right? Probably a nitrate, something very innocuous that's not going to react with anything else, right? So it's not just positive charges floating around in there. There's some negatives balancing things out as well. All right, so we had 9 to start with, and we were able to separate them based on their chemistries into 3 different groups. Group A was isolated first because when we added the ammonia, they formed insoluble hydroxide salts. This included our aluminum, our iron, and our manganese ions. You need to know your charges on these as well. So these form insoluble hydroxide salts. Now, the reason that happened is because, again, we had the aqueous ammonia, which means that we had hydroxide ions available in solution. Should always include our states. Okay, so this is where the hydroxides came from that made these come out of solution. We were able to further separate the aluminum from the other 2 because when you add more hydroxide, aluminum that was solid, excuse me, forms this aqueous complex there. Okay. The other 2, iron and manganese ions, we were able to redissolve when we made them acidic, separated them, and did their confirmation tests. So you need to know each step, just again, not specific quantities of amounts that you added, or concentrations that we added. So separated out group A, that means we had a mixture of the other 6. So this was our first step. Our second step, we went through here, we added ammonium carbonate to it. Now at this point, these formed insoluble salts, hydroxide salts. So we had group B and group C ions left in solution. Group C is our copper, cobalt, and nickel. They're special because they form ammonia complexes that are soluble in water. So when we added ammonia up here, these formed special soluble complexes. Okay, so these form stable ammonia complexes, and they're soluble in water.
So, in my mind, that just means that it dissociates, so they're not.
No, so they form, if you look on, lots of pages I can pull out here. If we look on the bottom of page 72, right, they gave you the list of the complexes. So they're in a special complex. So for instance, copper forms this complex, which has a charge. It's still a type of ion. It's just got other ammonia surrounding it and interacting with it. So it's in a different form and it's soluble. But because it's in a complex with ammonia, it's not going to form a hydroxide salt or precipitate out or anything like that. This is keeping it in solution.
Okay.
It's a stable complex.
Okay.
Group B ions don't form that complex. They're just staying soluble in solution at this point. So group B was our barium, our calcium, and our magnesium. Okay, these are just in solution. They're aqueous still at this point, but they're not associated with anything else. What happens with our group B is we can add that ammonium carbonate, and barium and calcium form insoluble carbonate salts. So those two will be separated out. Magnesium is a special case, as it does not form a carbonate salt that is insoluble at the concentration that we're adding. So we pull this one out. We add so we've had the carbonate added, and we add the sodium hydrogen phosphate, and that forms a special complex that works because magnesium is 2+, ammonium is 1+, and phosphate is 3-. So the 3- has 3 positive charges to react with, and you form this special complex. And this is a solid.
So you said when we add the carbonate at the specific concentration we added it
pulls these two out of solution.
Okay.
Magnesium stays in solution until we add the sodium hydrogen phosphate, and then that pulls out a special complex that gets formed.
Okay.
Thank you.
Yep, you're welcome. Good luck on your test. So we're left now with group C. They're in solution as stable ammonia complexes, but because they're with that ammonia, they have a hard time reacting with anything else because they're in a stable complex. So our third step is we heat the group C. What happens when we heat group C?
The NH4 evaporates.
The NH4 evaporates as ammonia. It
The
converts
ammonia.
to ammonia.
Okay.
With any of the water that's present there, or you can think of it as reacting with any of the hydroxide that we have, and it's going to form ammonia gas. Actually, I'm going to write it that way. Not with water, but with the base that's present. It's going to form the ammonia gas and water when you heat it. Because remember, at this point, we have all sorts of things in solution. Everything we've added that has not precipitated out is still in solution. So we have ammonia present from up here. We have some of the ammonium carbonate that could still be present. So we could be getting rid of a little CO2 at this point also. We're getting rid of any of the water that made all of our solutions at that point. We probably have a little of the sodium hydrogen phosphate left in there. So there's all sorts of other ions that are present. We could have some hydroxide left from our original reaction up here as well. So there's all sorts of stuff going on. When we heat it, we're driving the reaction this way because it's an endothermic reaction. So we are evaporating our ammonia, evaporating water. So these are no longer in a stable complex. At that point, we add a little acid in solution to redissolve our solids, and then we do our tests on what we have left.
So why did you label it change in group C?
Heat.
Oh,
That starts.
heat.
This also stands for heat.
Heat, okay.
You were heating group C.
Okay.
That's why I have it here too.
I see. Thanks.
Uh-huh.
And this
Yeah.
gets rid of, so primarily we want to get rid of the the ammonium,
Ammonia.
and then, but it also kind of works to get rid of like the other impurities that we have, like OH. or
Not
hydroxide
everything,
or-
but it's going to get rid of the ammonia, water, maybe a little CO2. Everything else, any of the phosphate ions, those are all going to still be dried with
Okay.
the group C ions.
So it sounds like if we don't have to answer because it gets rid of all the other impurities, just
Yeah,
the,
just ammonia. We're really concerned about ammonia because removing that ammonia will break up these complexes, and then you'll have the ions available for these other tests.
oh. Okay,
right?
that
We're
was
getting
the
rid
light
of our
bulb.
stable complex by getting rid of the ammonia.
Okay, I didn't realize that.
Yep.
Now I see that. Okay.
Yeah, I can put that here. Break up complexes. So it can react with tests. So, other big thing with these qualitative analysis part, make sure you know how to write net ionic equations, right? Practice your net ionic equations. As you know from doing the lab report, right, there are a lot of net ionic equations. So make sure you understand how to write those.
So, I'm sorry, but when we did the acid and the litmus paper thing, that completely threw me for a loop. I was like, I don't know why I'm doing this, but I'm doing it anyway. And
So that was for, nope, that's not the right one.
With group 1, I think for group A, we did that litmus test for
Mhm.
HNO3.
What was I? Was I
Check the
testing
pH.
for something? Was I
You were making sure you lowered the pH
making
enough
sure? Okay, that's. And if it, okay,
Yeah, because
so that
we
the
are
reaction
adding-
could occur.
I think we are adding acid drop by drop, so that's why we
Mhm.
want to make sure.
Where did I put it?
That's for iron and magnesium.
Yeah. Yeah, so over here, so just making sure we're making it acidic enough
okay,
to make sure that we, because if we have our iron and we're adding acid to it,
yeah.
right, that's going to
Free up the
free up your iron
iron. Yeah.
and your form water. So it's just a way to dissolve our iron hydroxide from solid
Okay,
to aqueous.
okay. Otherwise, it would have
Right.
not
So
been able to react.
if you didn't get it acidic enough of this might not occur so that you wouldn't have enough of this for your conservation
Okay.
test. Yep.
We should not know this equation, this was just to make a concept.
Well, no, you need to understand the chemistry behind what you're doing.
Okay.
So it was one of your lab report
Oh,
questions.
Okay. This one.
Yeah. Nope, good to ask. So be able to use your KSP values to decide if something's insoluble or more insoluble than something else, right? Which one has the higher solubility. If you're asked about a math question, for instance, will something precipitate out of solution? Be able to understand how to solve for your Q, your quotient, and compare it to your KSP to decide if it's going to be a precipitate or if it's going to stay in solution. The other one that always seems to throw people was so figuring out which one precipitates first, right? In this case, the smaller the value, it's going to precipitate first because that means you have less things that ion. So something that's 10 to the negative 11th will precipitate before something that's 10 to the negative 8th when we look at a K. Because again, it's an equilibrium constant. So the bigger your K, the more products you have. In this case, that's ions. Because we're going from something solid to ions that are in solution. Okay? If it asks you the best way to separate ions, meaning you need to calculate solubility of one compared to something else, know that you don't just give an answer if it takes this molarity. That doesn't tell me anything. You might say, at this molarity, such and such starts to precipitate, therefore you want to stay just under this molarity to make only A come out of solution, or whatever, you know? So make sure you look at, that's like number 5 from your lab report for part 2.
Okay.
Make sure you review that and understand how to indicate what's happening in that solution. Always explain. It's better to give more explanation than just a yes, no, a number, whatever.
So in question 5, barium will precipitate first because it has a smaller value.
Yes. And then for the second part of that, you want to have a concentration just less than 9.1 times 10 to the negative 4th molar, because above that value, the calcium is going to start to precipitate, or whatever, yeah, the calcium one. Yeah, that's what I got.
Cool.
Any major questions? I'll be here till 11:30. Sunitha's really good.